Hello, welcome to Forest Learn. In this video, you can try a 1-mark question to do with motion graphs in SHM, or simple harmonic motion. Once you've had a go at the question, we'll discuss the solution so you can check your answer. Let's take a look at the question. A particle is performing simple harmonic motion, SHM, with amplitude A and angular frequency omega. Its displacement time graph is shown below, so down here. Sketch the acceleration time graph of the particle, showing the maximum and minimum values of acceleration. Please pause the video here and have a go at the question by yourself. Once you've had a go, unpause the video and we'll discuss the solution. Okay, welcome back. As you follow the solution, it's a good idea to make some notes of your own, especially if you found the question tricky. This makes for a more productive and active learning process and is better than just listening and watching the video. The simplest way to answer this question is to remember the equation that defines SHM. Recall that if something is undergoing SHM, then the following equation holds true. A stands for acceleration, X stands for displacement, and this curly looking W is omega, which stands for angular frequency. What this means is that if you know X, you can find A by just multiplying X by minus omega squared. So when X is equal to 0, as shown by these black points here, A is also going to equal to 0. And we can show this on a graph of acceleration versus time. So these 3 purple points down here are in line with these 3 black points up here. On the other hand, when X is equal to capital A, the amplitude, we can plot the acceleration directly below to be at minus omega squared times the amplitude. In other words, if we replace X here with capital A, the amplitude, the acceleration is minus omega squared times the amplitude. That's what we've got here. Similarly, if the displacement is equal to minus capital A, then we can plot the acceleration at that moment in time to be equal to omega squared times capital A. Now we could continue doing this, but you can probably see that if we were to just connect up the points and fill in the gaps, we'd end up with a graph that looks like this. This is just a sine graph, and you can see the maximum value of acceleration is omega squared times capital A, and the minimum value of acceleration is minus omega squared times capital A. And so we've answered the question. What the SHM equation tells us is that acceleration and displacement are directly proportional to one another, meaning that the acceleration time graph will be the same type of graph as the displacement time graph. So both of these graphs are sine graphs fundamentally, except the acceleration time graph is a reflection of the displacement time graph in the time axis. The reflection is due to the minus sign in the SHM equation. You may be wondering how it is that the displacement time graph looks like what we've drawn and not this, which is probably what you're familiar with your studies on SHM. But notice that if we were to pick a different starting point on this graph, so for example here, and we were to draw out one whole cycle, we would just get the displacement time graph that we've been looking at in this question. In other words, these graphs are fundamentally the same as each other. They just correspond to picking the start, or t equals 0, at different points of the oscillation cycle. A more mathematical way of seeing that the original displacement time graph here truly does correspond to SHM is to note that the formula for displacement is given by x equals minus a times sine omega t. And from this it's possible to deduce that the velocity of the particle is given by this expression here. If we differentiate x, we get v, and we end up with this. And once we have this, if we differentiate again, we get an expression for the acceleration of the particle. And note here that there's a similarity between this and this up here. Indeed, you should be able to see that what we've got here is simply equal to minus omega squared x, which is simply the equation for SHM. In other words, what we've proved is that a particle whose displacement time graph is given by this is indeed performing SHM. If you found this video useful, please like it, share it, subscribe to the Forest Learn channel if you haven't already, and leave a comment. I'd love to hear from you. Thank you for listening, and I hope to see you soon.